Good morning, everyone. It's 8 a.m. on a beautiful San Francisco morning. Thanks for joining us. What better way to start your day than learning from two innovative companies about how they use machine learning at scale to solve real-world problems. My name is Bora. I have the pleasure of being accompanied by two of my co-presenters, Gandalf from Discord, which you'll hear from soon, and Daniel from Tamr. I hope our session will have something relevant to everyone in the room because we'll go after different use cases. So independent of the industry you're in or where you are in the ML lifecycle or growth trajectory, hopefully we'll have something for you. First, Tamr will talk about how they offer a data platform for enterprises who are trying to work with data quality issues, especially as they merge data from disparate sources. Then we'll have Discord talking to us about how they built this machine learning platform for the data scientists and app developers, where they can more effectively collaborate and reuse the data and serve low latency real-time predictions to their users. Sorry. Okay. But before we do that, let's talk about Bigtable, the database that is behind a lot of these use cases that we're about to go through. This clicker is very confusing. Google offers many different databases. Some of them are relational databases, some are NoSQL databases and caches. And depending on where you are, sometimes you may want to use third-party engines in Google Cloud, like Oracle, SQL Server, MySQL. Google also has its own databases that is homegrown, and Bigtable falls into that category. And we may say it's one of the most influential because it was arguably the database that led to the NoSQL database movement 18, 20 years ago, which led to open source projects that are very popular today, like Apache Cassandra and HBase. They were inspired by Bigtable. And Bigtable has been in production and continues production for the past 18 years at Google. And it's the database behind a lot of Google's billion user plus services like Google Analytics, Ads, Search, Maps, YouTube, et cetera. It currently serves about 6 billion queries per second and handles over 10 exabytes of data. And for the past 8 years, Bigtable is also available as Cloud Bigtable to Google Cloud users. And it's used by some of the world's largest brands online, from social media to streaming to financial services, crypto, you name it. So Bigtable offers consistent single-digit millisecond latencies and high read and write throughput. And you can deploy it in a multi-master, multi-primary setup where you could have clusters across the world in a global deployment to further reduce the latencies. If you're serving users and you can bring the data closer to them, it helps you reduce the latencies further. As a result of this, it's good for many different use cases. But since we're talking about machine learning today, I'll highlight some that are immediately relevant to machine learning. So in the domains of ad tech, retail, and media, personalization, for example, is one example of this. And if you want to learn more about how this works, Google Ads published a paper on Google Cloud Blog last year, which goes into the details of how they use Bigtable for serving personalized ads at scale. Across financial services, IoT, and other areas, again, feature store, online feature store is a very common use case. It serves different use cases like fraud detection and credit decisioning. We also see a lot of Bigtable usage in IoT telemetry for stuff like alerting and predictive maintenance, where Bigtable's high read and write throughput becomes very handy. And we have even seen use cases where our users got creative with hashing the row keys, and they use Bigtable for things like embedding search, near duplicate detection, et cetera. So I walk you through some Bigtable use cases and a quick overview. Let's hear from Daniel about how they use Bigtable in production.
All right. Ooh. Thank you, Bora. Hi, everybody. Good morning. Very excited to be here, opening for LL Cool J. Never imagined in a million years that would be happening, but here we are. All right, let's see. Let's see if I can figure out the clicker. There we go. That's my generative AI right there. My name's Dan. I am a co-founder of Tamr, and today I'm going to tell you about Tamr and Bigtable, unsurprisingly. And we began to adopt Bigtable along with HBase about 5-6 years ago. And it's been a huge success story for us from a technical adoption perspective. And our usage of Bigtable as a system and as a key component in what we do has grown and grown over time. So it's a fun story. Let's get into it. First, let me introduce you to Tamr and who we are as a company. Tamr is the world leader in ML-driven data mastering and data unification. We were co-founded by, among others among myself, by Mike Stonebreaker and Andy Palmer, who previously co-founded the company Vertica Systems, another large-scale distributed database. And Mike, as you may know, is the Turing Award winner for his contributions to the field of database systems. So it goes without saying that we're folks who know a good database when we see one, and so that's part of why this is cool. Now, what we do at Tamr is we take data, which generally speaking is a huge mess all of the time, and we turn it into something useful. We take data and we apply all sorts of different techniques to clean it, enrich it, combine it, match it together, so that you can get high quality outputs that are actually actionable for a business. We do this within large enterprises, and we do it by applying machine learning and artificial intelligence techniques to essentially deliver results faster, at lower expense, and with just generally better results than you could achieve using traditional methods. Our product and our engine is based on over a decade of research and development in this field of applying machine learning and probabilistic methods to problems in data integration. And our product bakes all of that in and presents it in a way where end users can take advantage without themselves needing to hold a PhD in machine learning or neural networks or anything like that. Now, that's a little bit about Tamr. Let's get into some of the context of how we use Bigtable. I'm going to go through general context for why we chose Bigtable as a system and as kind of a cornerstone of our product in the first place. And then I'll get into some specific highlights of experiences. I'm hoping that that range of content will appeal to folks who are completely brand new to Bigtable on one hand, as well as to practitioners who have been playing with it for a long time. So first of all, some high-level architecture. This is Tamr's solution architecture from 30,000 feet. It's fundamentally a very simple picture. On the left-hand side, you have source systems. So within a large enterprise, this is anything that holds data or generates data. So applications, databases, APIs, services, whatever. We're going to load all of that data from these sources into our system, process it, improve it in a myriad number of ways, and then we're going to take those improved results and deliver them to downstream systems on the right here. So that could be BI tools, applications, services, APIs, AI models, data warehouses, you name it. So fundamentally, this is a picture of a pipeline. And it's take data from point A, process it, make it good, put it down in point B. But the architecture is also, in a way, a stateful database. We store results and intermediate results from these processing pipelines so that we can support features like incremental updates, so that we can provide APIs and a user interface where users can come in and interact with the data and improve the pipeline and the process as they go. And we can also act as a system of record within a context of master data management. So all of that depends on being able to take this large mass of data that's kind of in-flight processing and store it within a distributed database engine that can support all of the workloads that we need. Looking inside the box, this is some of our internal architecture. I want to focus really on the bottom left corner here, which are the 3 pillars of what we call our data plane. So these are Cloud Data Proc, which provides distributed processing in Spark. It's Bigtable, which is our primary storage for data scale artifacts. And it's BigQuery, which we use for views and ad hoc queries that support features within our user interface. Now, let's talk about the problem that we're solving and why it's so critical to have a highly capable distributed storage system within it. The most compute-intensive problem that we solve is clustering records, matching records across all these different source systems, and doing it in a way where we don't have a join key. This is essentially a fuzzy join, where we're using probabilistic techniques and an ensemble of models to learn what constitutes a join. And how do we map records from all these things to the same real-world entities? So that's fundamentally an n-squared problem. You need to compare every record to every other record. Algorithmically, of course, we don't do all that, but if you want to achieve high recall, you really do need to explore a large portion of that quadratic scale space to be successful. We do this on data sets that contain billions of records and that are updated millions of times daily. And so we need to be able to handle processing workloads that can apply our pipelines at that scale. Our system supports sub-second ad hoc matches and updates, so that's another layer that needs to be added into this. So at that scale, we need a backend that's extremely performant. So Bigtable satisfies all of these workloads. It supports the high throughput batch processing that we need, both in terms of reading and writing data. It supports targeted incremental updates, either within pipelines or via APIs. And then it supports low latency interactions and point queries and all sorts of the good lookups you get from a highly capable key value store. But it doesn't just satisfy the requirements of our workloads. It really has these major advantages that put it over the top compared with other systems in the domain. First of all, it really sits in this optimal position in the trade-off space. Thanks to the internal architecture of Bigtable, and this is what Bora was mentioning about why Bigtable kicked off this NoSQL trend. It's capable of essentially write performance and read performance does not degrade with the scale of data stored within the system. And that's critical for us because we're writing huge amounts, huge volumes of data, and we need to make sure that the system doesn't suffer the more that the user puts in it. Another key advantage is the elasticity of Bigtable. You can scale it up and down based on workload. It has an auto-scaler built in, or you can manually resize clusters on the fly. And I'm going to talk first in a second a little more about how that gives you free performance. But the really critical thing, just fundamentally, is that allows us to balance batch workloads with low latency query workloads and handle both of those together in a way where we can still meet our SLAs. Finally, as a managed service, the total cost of ownership of Bigtable is just, it's like orders of magnitude lower than running comparable systems yourself. We also support HBase and Cassandra, and Bigtable makes things possible on Google Cloud that are simply unthinkable on other clouds or operating on-prem. All right, so that's kind of the context on why we chose Bigtable. Let's get into some of the details of our experience with it. Just some quick and dirty numbers. This is like a typical customer deployment. We're processing about 15 terabytes of data, can range between 10 and 20. And we're gonna have a background query load of about somewhere between 4,000 and 8,000 queries per second, targeting a P99 latency of 10 milliseconds, which we typically achieve at this scale with just a small 3-node cluster. So extremely performant, extremely reliable. Then customers will run periodic batch refreshes. So let's say like a weekly refresh of all of the data to incorporate holistically whatever's changed. And when we do that, we'll launch a Spark cluster that's going to do all this processing back and forth, hammer the system, and so the system will scale up to, let's say, a 30 node maximum, and give us extremely high throughput while still allowing us to hit those latency SLAs for the interactive query load. Now, this I think is some of the cloud magic that Bigtable brings and that Google services kind of bring in general. Essentially, if we extensively use elastic and ephemeral resources within Google Cloud. So when we run large-scale pipelines, we're going to spin up a data proc cluster on the fly just for the purpose of that pipeline. And we use auto-scaling within Bigtable. So what we're able to achieve, so the chart on the left is showing runtimes for clusters of different sizes. And what you can see is that essentially, we're achieving near linear speed up while we're scaling up the size of the hardware that we're throwing at these pipelines. So that's great. It means that the problem is well parallelized. What's really remarkable is the chart on the right, though. So this is the cost of the runs for those different size clusters. And what you can see is that the cost on the large cluster is, within 10% the same as the cost on the small cluster, but it went 3 times faster. So it's because we're parallelizing the problem very well, achieving extremely high utilization, we can throw more resources at the problem, solve it faster, and then get rid of those resources and stop paying for them. And so this is some of our secret sauce. This is amazing. Last thing, I just want to share some lessons that we've learned from working closely with Bigtable and these kinds of use cases. First, and I think this is Bigtable 101, is that key design, how you design your primary keys, is critical. This is especially true for batch processing use cases. If you want to get good parallelism, like we saw on the previous slide in that linear speedup, you need to use key design that's going to spread the data across the whole cluster and give you that lift. If you're doing that, one neat trick that we learned that will speed up your write throughput by a factor of 5 is to sort batch writes. This is something nuts that we sort of stumbled upon. This chart here is mid-experiment. The thing on the left where it says April 23rd is without this trick. And then that spike that's off the chart is we made a 1-line code change and we're holy crap. So basically, if you're hashing your keys, it's going to spray data all over the cluster. If you sort your batches, it reduces overall network load in the service layer, and amazing things happen. So definitely do that. Finally, this is sort of an unexpected advantage that we discovered as we worked closely with Bigtable. It's an amazing platform for performance engineering. It comes built in with a wide set of tools around observability, metrics, and the key analyzer that give you just an incredible developer experience. So it's great to just dive in, get your hands dirty, and that's it. All right, thank you. Gandalf, take it away.
Thank you so much. Didn't know about the sorting, and we might have to do some work later today.
That's good.
Well, thank you all so much for being here. So let's jump in. So first of all, I'm very happy to be here today to talk to you about how Discord leverages GCP technologies, specifically Bigtable, for a feature store. My name is Gandalf Hernandez, and I head up the ML platform team at Discord. But first, if you're not familiar with Discord, Discord really is about giving people the power to create space to find belonging in their lives. We want to make it easier for you to talk regularly with the people that you care about. We want to help you build a relationship with friends and communities, even if they're local or if they're across the globe. In the 8 years since we launched, we built up a dedicated user base, over 150 million users that interact in over 19 million communities. Some of our communities are huge, You may have heard of Midjourney, for example. But many are small, groups of friends, classmates, people who share an obscure hobby. I've come across people who build 1970s synthesizers. I've come across people that are very, very particular about the Magic the Gathering rules that they play. They find their communities on Discord. So what about machine learning and Discord? We use machine learning to keep our users safe and detect potentially harmful and abusive content, and also to keep unwanted actors out. We also use machine learning to help keep our users up to date with what they care about and help them find new communities. But machine learning is nothing without data. And data is nothing without a fast, reliable, and scalable way to get at it. And that's why we're here today, to talk about how we are building our feature store at Discord using Google technologies. But before we jump in, what is a feature store? And in case somebody here is not very familiar with machine learning, a feature is a piece of data that is used as an input into either training a model or once you have trained a model to make a prediction. To us, a feature store is a layer on top of our existing data warehouse to present the data in ways that make sense for machine learning. The feature store makes it easy to access data for machine learning training and abstracts away the complexities of where the data is stored, of how to make predictions at real time at high scale. And also a feature store should make it really, really easy to discover and understand features. Features can be accessed in multiple ways. Data scientists, they love to use Jupyter notebooks and want to easily consume them via Python as they build, evaluate, and iterate on their models. Our backend and machine learning engineers need them in real time to make prediction based on user actions at scale when you have tens of millions of users that are online at a given time. Our underlying data warehouse at Discord is BigQuery based, but we don't want our machine learning engineers, our data scientists, to have to craft complex BigQuery joins to get to the data they want to have access to. Specifically, we want to give them an API that makes it very easy for them to do time travel. Time travel is the ability to access feature values as they were at a particular point in time in the past. So you want to say, at time t, when I'm looking to make a prediction, what are the values of all the features that I care about? Some might have happened a second beforehand, some may have happened a day beforehand, and these queries can get extremely hairy if you do them. And if you mess up, you start pulling out data from the future. Your machine learning model, when you train it, it's going to work really, really well. When you put it into production, it's going to work really, really badly. And this is, it sounds funny, but it actually is a real, actual problem when you have data that lines up along different time scales. So we wanted to just fully abstract that away and just gives our user an API saying, give me all the values up to time t for what I care about. Another thing that we see is in machine learning in general is that a common anti-pattern, if you don't have a strong feature store, is that each team, or even individuals within a team, will do the exact same feature engineering. They'll recreate the same data point over and over and over again. They may even find something and say, well, I don't know, do I trust this? I'll just make my own. Additionally, in a typical data warehouse, the main unit of abstraction is the table. We look for a particular table and we say, well, what are the keys on it and so on. But in machine learning, the key abstraction is the feature, or if you're mapping that to a database paradigm, it's really the column. If you're looking for the popularity of a server at Discord, you shouldn't have to care that that table also has the category of the server or some other metadata about it. What you really are looking for is, I need the popularity of the server. So we're trying to abstract that away and have users think of it in terms of individual features that are keyed off of individual keys. So, what do we know about our users? What do we know about our servers? What do we know about our user and server interactions? And they could all come from different tables, but we want to present a unified interface to our users. When the feature store becomes the main level of abstraction, it makes it a lot easier for discovering features. It makes it easier to reuse features. And by making this access easier, our data scientists are much more likely to share features because they can pull it out, run some simple analysis on it, see that it serves its needs, and then use it. We also need very strong support for real-time features. If a great moment that is happening that we think our users will love, we need to tell them right now. We can't tell them, hey, yesterday there was this awesome conversation that we really thought you would have loved. No. Same word if there's a bad actor happening or there's spam happening, we need to detect that as soon as possible. And we want to be able to, again, abstract this away from our users. A consumer of a feature shouldn't have to work with the feature in different ways if it was created in real time or if it was calculated in batch. Also, Discord has had great success building on top of BigQuery for a data warehouse and Bigtable for multiple use cases, and we want to continue with that. So therefore, it was very important for us that we were able to leverage our feature store on top of BigQuery and on top of Bigtable. So let's take a little bit of a look at our architecture here. As mentioned, we use BigQuery for our offline store and Bigtable as our online store. We support 3 different ways of generating data. You have all batch, which could potentially be considered traditional machine learning. Features are calculated periodically, daily, hourly. In our case, we have jobs that are calculated every 15 minutes, uploaded into a feature store, and then used for serving. This model is pretty easy to implement. You could use BigQuery, you could use Batch Spark or Dataflow or any other job, but you don't have the real-time aspect of it. The second version is the Lambda architecture, where you have slow-moving complex features still calculated in batch, in our case, using BigQuery, while now you're starting to bring in real-time feature engineering. When was the last time the user sent a message? What was the last server they interacted with? And we merge them together in the feature store so that a model that needs to make prediction or an engineer that is working on a model, they access the data in the same way. They don't have to think about if it's real time, I need to go over here. If it's batch, I need to go over here. And the third way is the Kappa architecture, where we're now moving everything to real-time processing. So events are coming in, we process them, but in order to bootstrap events, where sometimes the features need longer history, this is specifically true, especially true in the safety domain, where you may have events that are very infrequent, but you need to react to them very quickly when they come in. So in that case, we blend our feature engineering streaming pipeline, where we feed it using batch data stored in Iceberg, blended in with the real-time stream coming in via PubSub. This unifies where the feature calculations are done, and we avoid this kind of mismatch of trying to have one slow-moving version of a feature and then a fast-moving version of a feature and training on both of them. But again, the key when building out this feature store is that our users don't have to care about how the feature was generated. They may want to know that this one is updated as soon as an action happens, but in the way that they write their code and the way that they access the data, it's all unified. So let's talk a little bit more specifically about Bigtable. We do take advantage of Bigtable's multi-zonal features for availability and durability. We rely very heavily on Bigtable's auto-scaling capabilities. We have one cluster that is used for writing batch data. It scales up heavily when we're doing ingestions. And then we have 2 read clusters that are used for the real-time serving. And then we use Bigtable's replication features to get the data over. All of our Bigtable data today is read-only as far as like customer interaction part is concerned. So we could, in most cases, recreate the data. Latency requirements varies from use case to use case, but Bigtable is really not a significant source of latency. We're seeing P50s on the order of 3 milliseconds, and our P99s are typically around 10 milliseconds. But they do spike up to 50 milliseconds when we're doing ingestions. We know that we can get this down lower, but frankly, it really hasn't been a priority, and Bigtable is not a big source of latency in our system. We take advantage of Bigtable's time to live feature to clear out all data, which saves us the efforts of having jobs to purge out stale data. And we're currently actively working on integrating Feast with the Feast feature store, and we're moving our existing real-time system onto Feast. Both BigQuery and Bigtable have showed their strengths, and we're very excited to keep working on them as we keep building out our feature store and ML capabilities at Discord in great partnership with Google. And that is all I have. Thank you so much. And we are hiring. You have my name. Hit me up on LinkedIn, and let's talk. Thank you so much. Thanks.
Okay, so you heard about these great use cases, and you heard about some complaints, like I'm doing writes, it impacts my read latencies, et cetera. I'm happy to announce, if you want to implement similar solutions yourselves, things will get better. So this is the chart both Gandalf and Daniel were talking about. If you run everything at the same job priority, sometimes if a heavy batch write or a heavy batch read comes in, you may have some low latency serving workloads that will get impacted. In this case, left side is before and right side is after this new feature we call request priorities. When a heavy batch write comes in, if everyone is running at the same, everything is running at the same priority, you can see these P99s go to, in this case, it's 4 seconds from your typical sub 10 millisecond latencies. But with the request priorities, which is in preview now, and we'll have a blog post that will come out tomorrow that will have links to sign up for all of these features that we're talking about here, you'll be able to run those jobs, batch reads or writes, at low priority while your serving workload is running at high priority. Then we'll be able to throttle, spread out, deprioritize those batch processing jobs. That way you will see the chart on the right-hand side where the impact when those jobs kick in are barely noticeable. And if you combine this with auto-scaling, things will get even better because this is a way of absorbing things by spreading out the load. What if you have to load more? Then you can turn on auto-scaling. We'll also combine that with this. So we're very excited about this. This simplifies a lot of things. You don't have to copy your data out to do heavy batch processing to other systems. So it simplifies, it reduces the cost for you. Of course, anytime you take the data out, you have the problem of things going out of sync. Want to serve it, I have to publish it, materialize it into an online store like Bigtable. And this is a very common flow. And you've seen this in a chart like 3 minutes ago. Gandalf had that. But you need to have data pipelines. It could be a data proc cluster, data flow, cloud composer. There's some sort of an ETL tool that you have to configure, pay for, have a data engineer work with you. So there's a lot of impedance there. And if you want to innovate, you want to move faster. So we worked very closely with the BigQuery team to build this directly into BigQuery. Now you'll be able to write a SQL query and just export directly from BigQuery. There's no tool in the middle. You could do this using the APIs. You can also use the UI in there to quickly convert your SQL code into an ETL job. And this comes with a lot of flexibility. Again, another feature currently in preview. You'll be able to even schedule these things. You could say, I want to run this job every 15 minutes. BigQuery has this appends table value function that will give you things like what happened since this time, so you can look at deltas and even figure out how to write those deltas only into Bigtable. So it gives you a lot of flexibility. A few clicks, you go from a SQL query into an ETL job. So again, you will have links to this in the blog post, but since this is such an easy feature to adopt and play with, we also made it convenient and added a QR code for you if you want to take a picture of it. You can sign up and we'll happily give you access. And I think, again, with this feature and more that I can't even mention because we are out of time, a lot of the things that we discussed, these use cases will become a lot more easy for you.